All right, the central limit theorem, also called the classical central limit theorem, or sometimes called the Lindbergh-Levy theorem. Okay, there are several versions of the central limit theorem, some more relaxed than others, but this is the sort of the common classical central limit theorem that's in most of the elementary texts and used in all the probability and statistics classes, at least at the undergraduate level. So let x1, x2, up through xn be independent and identically distributed random variables coming from any distribution. Any distribution. They're all coming from the same distribution. They all behave the same way. They're all independent, but they can come from any distribution with mean mu as long as the variance is finite. Then, you might remember that sometimes we use this notation xn bar to mean the sample mean, right? It's the average of those guys, and also remember that the mean of the sample means, you should know that is the expected value of xn bar, is just the population mean. We've already proven that, and you also should recall that the standard deviation of the sample means is the population mean over the square root of the sample size. Okay, none of this is new. We have that it turns out that the probability that the sample mean minus the mean of the sample means divided by the standard deviation of the sample mean, the chance that that is less or equal to some number, like we'll call it little z, this probability converges as n goes to infinity, as your sample size gets big, to the chance that a standard normal is less than or equal to that number little z. Okay? Now, if you look at this over here, all this is just standardizing the sample mean. Okay? I'm subtracting off its mean and dividing by its standard deviation. So it's just bringing this sample mean down around 0. Okay, so that the distribution of this thing is it's centered at 0 and has standard deviation 1. Another way to say this, there's several other ways to say this. One way to say it is that it's the chance that, of course, if I just substitute in what the mean and the standard deviation are for the sample mean, it's just this, right? So sometimes you see it written like that. Okay. Another way to say this is that maybe you want to think instead of in terms of sample means, maybe you want to think in terms of random sums. Okay, so if you're adding up the weights of a bunch of railroad cars, maybe you want to know the chance that the total weight exceeds a certain amount. Okay, and you can see that this statement is the same as the one above it. Just multiplying through top and bottom by n there, you get exactly this. Okay, and also finally you can also think of it like this: the sample mean, the random sample mean, behaves approximately normal with mean mu and standard deviation sigma over root n. for a large sample size. Okay. Now the magical, mysterious part of all of this is that, in fact, you can be sampling from any distribution. You can be right skewed, left skewed, bimodal, whatever, as long as the variance is finite. Okay, and you get this really nice result.